Hello, my name is Andrew Leonard, and this is my final project for ME 7751 Computational Fluid Dynamics, and I'm solving Falker-Skan boundary layer problems with fourth order Runge Kutta method using shooting. So different examples of classic boundary layer problems are the Blasius case, which is effectively just a flow driven parallel to a flat plate, and also the Hemans boundary layer, which is on the other spectrum a flow going perpendicular to a flat plate. And Faulkner-Skan is effectively the Blasius case, the Hemans case, and everything in between. So it's the flow over a wedge going from an angle that is determined by this beta. So for example, we can have if beta is equal to 0, we have the Blasius case. If beta is equal to 1, we have the Hemans case. Now we have the different governing equations. So the first equation is our continuity equation. The second equation is the x momentum equation, and the third equation is the y momentum equation. In the third equation, we're effectively just saying that the pressure gradient along y, which is the direction perpendicular to the flat surface of the wedge, is 0. And when we're looking at the x momentum along the flat plate or along the wedge, we can ignore a lot of the viscosity terms, given that we are analyzing the flow not near the plate, but the flow further away from the plate. And as mentioned before, if we set a beta equal to 0, we recover the Blasius case, and a beta equal to 1, we recover the Hemans case. And what we notice is effectively we use a similarity variable that we'll mention later, and we recover this similarity solution. So this is actually the governing equation we will be solving, and we'll be solving for one similarity variable. Now we employ the fourth order Runge-Kutta method to solve our similarity equation. And the Runge-Kutta method effectively defines four different coefficients that are based on the step size h and the function at different points. And it's important to note that we're solving the equation y, and that y prime, we define it as f. And so we take the coefficient k1, so the function at, or the derivative at the current point we're analyzing, and we're evaluating these coefficients at different points further along the domain. And we accumulate these points onto this formula, which gets us a fifth order, or h5, h to the fifth, the order of h to the fifth, and we're able to evaluate the next step. So this can be either in a time domain, but in our case, we're evaluating on a spatial domain, so in the x direction. So we have our governing equation from the previous slides, and what we do is we manipulate it slightly. We keep f as f, but we define a variable g as f prime, and h as g prime, or in other words, as f double prime. And what we achieve here is an equation linearized in h, and we use this with our Runge-Kutta method. So we solve the Runge-Kutta method separately for f, g, and h. So the coefficient, we have these indices 1, 1, 1, 2, 1, 3. So the first index is what we would say like which coefficient within the Runge-Kutta method. So the first, second, third, or fourth. And the second index is regarding which variable we're solving for. So the index 1 is we're solving for f, index 2 is we're solving for g, and index 3 is we're solving for h. And we have h prime defined here by this governing equation, so we can just solve for that within the k sub x3, or anything with a k sub 3 component. And then the K1 and K2 components are very easy to solve. It's effectively just delta x g, and then the coefficient that corresponds to that. And yeah, it's important to note that we use delta x instead of h since we're solving on a spatial domain. This is our step size that we define in our code. So as mentioned, we compile the different components, so K11, K22, K21, K31, so on and so forth, to solve for F, we solve for G, and then we solve for H as well differently, or separately. And we can see us doing this within this loop within our code down below. Now, we need to employ the shooting method for the reason that we do not know a starting value for H. We do not know our initial condition for H. We know that f and g are equal to 0, given that, well, g is equal to 0 since the velocity at the start of the plate is equal to 0. That's why we're defining that. And we don't know what h is initially, but we do know one piece of information that can help us get there is g at infinity is equal to 1. So effectively, it's the free stream velocity, as g is the dimensionless velocity. And we just assume that we're defining our domain within the similarity variables large enough such that g at the end of the domain is equal to 1. So while we don't know h, we can guess values of h that satisfy this condition, that g at the end is equal to 1. That's our sort of our boundary condition, so to say. So the way the shooting method works is first we employ two guesses. We overshoot the value of, we pick an h that causes this error function, 1 minus g, and I is the iteration that we're evaluating at. We guess one that makes the error function negative, so we overshoot it. And then we also make a guess where we undershoot it, so this error function is positive. And what we do is we use the bisection method to get our value of h closer to the correct value. So as you see here, we have this is the bisection method. We have a guess and a second guess, and we take the midpoint between those guesses. And then we'll run that, well, first we update our bounds. So our lower bound now becomes this new midpoint, or this new guess. We evaluate how close this guess of h gets us to this error function equaling 0. And then we iterate again. And we keep iterating until this error function is deemed to be small enough. And lastly, it's going to note that we compute this twice. So we first compute the shooting method and the Runge Kutta method for a small domain. That gets us a value of h that is closer to what the real value of h is. And then we expand our domain and then run the whole simulation again. The reason we do this is that if you compute this for too large of a domain, that sometimes there is instability and effectively you don't get a solution. So here we just visualize the shooting method within our code. So the error is less than a given amount that we set. And we compute the Runge Kutta method, compute the error. And if the error is negative, we change one of the bounds. And if it's positive, we change the other bound. We compute the new guess for h, which we call here p. And then we keep running it until the error satisfies our condition. So here we plot the similarity solutions, and we notice that for the Blasius case, we reach a free stream velocity, we would say slower with respect to the similarity variable than the Hemans case. And the similarity variable effectively scales with y over x, or to a degree. It scales to that. Not exactly, but to a degree. And one way to interpret this is that for larger wedge sizes, for a given value of x, if you go up in the y direction, you reach the free stream velocity faster for larger wedge sizes than with smaller wedge sizes. Another way to interpret this is that for a given x and y value, the velocity with respect to the flat plate would be faster for larger wedge sizes as compared to smaller wedge sizes. We also compare our results to published results from ANSYS on the Blasius case velocity profile. And we see that numerically, the results between our blue line and their line fit very well. And I would, to an extent, say that this effectively validates the results from these computations. So on the next slides, we actually parameterize the flow and the dimensions of the plate. And we also effectively take our generalized solutions that collapse onto one curve and test them for actual parameters. So here we take the boundary layer velocity, and it's defined by the free stream velocity, the x coordinate divided by the length of the plate raised to the m. And m we defined on the previous slide, which is effectively a function of beta. And we multiply that by 0.99, where the free stream velocity occurs. It's 99%, or sorry, where the boundary layer velocity occurs, it's 99% of the free stream velocity. And we notice that the boundary layer velocity is uniform for the Blasius case, which we should know from our previous courses. And the boundary layer velocity is effectively linear for the Hemans case. And as our wedge size increases or decreases, the increase to the increase of the boundary layer velocity is slower and slower. I would say the boundary layer thickness is the more interesting parameter to analyze as we use these variables here and multiply it by eta at 0.99. So what eta at 0.99 is the eta value at which we, on our velocity similarity solution, we reach the value of 0.99. So for each of these flows, we have to find what eta achieves a similarity velocity of 0.99, and we plug it into this evaluation. And we have our nu defined on our previous slide and our u naught also defined, and L as well, which is 1. And we see that the boundary layer thickness grows faster for the Blasius case, and as our wedge size increases, our boundary layer thickness decreases more and more. So that's one observation we can make. So yeah, thank you for listening to my presentation. These are my different references, and yeah, thank you very much.